Alright, today we are going to look at the unit vector and vector applications. So, in example 1 here, we're actually going to take one of the problems we did last time and approach it slightly different. Now, last time that we did this, we looked at the vector v plus vector w first, and actually we're going to go about this just a different way to find the true bearing and the true speed. Okay, so this is set up just like we did last time. So I'll have my vector v, which is 170 miles per hour. So that's my v. And remember, that's north, 40 degrees east. So there's 40 right there. And then I have my south 60 degrees east, and that is the 35, which we're going to call W. And this is 60 right here. Okay, so actually what we are going to do is, instead of adding right on top of each other to find where this vector lies, the W or v plus w, we know it's going to be somewhere here. So we're going to actually calculate this out without doing the adding first. I mean, we will add, but we're actually just going to find it from this vector here. Okay. So the first thing you want to do is look at your vectors in component form. So if we look at v, we have our magnitude of 175 times, and we know that we are doing cosine of the degree. Now I'm going to wait to put that down, times sine, or comma sine of the degree. Now, if you remember, when you find theta, it's not necessarily the degree we see, but it's from our starting point of 0. So if we look at v, vector v, this angle here is actually going to be 50. Okay, and of course we can multiply that magnitude out, and we get 175 cosine 50, comma 175 sine 50. And we'll do the same thing for w. Okay, our magnitude is 35 cosine. I'm going to keep that theta not there so we can look at it and what it needs to be. So we're down here, right? And this was 60. So this down here is 30, but since we're going clockwise, it needs to be a negative 30. Giving us 35 cosine of negative 30, 35 sine negative 30. Okay, so what are we doing to these two vectors? Remember, we are adding them. So I'm going v plus w. Okay. Now, what I'm going to do, guys, so I don't run out of room, is remember when we're adding, we add the x component together right there and the y component together. So that's what I'm doing right now. So our first part here is going to be 175 cosine 50 plus 35 cosine negative 30, comma 175 sine 50 plus 35 sine negative 30. Okay, I know that's long. Now, if you remember from last time, the true speed is from the magnitude. Okay, and how do we find magnitude? Well, that is the square root of the x component squared. And again, I'm going to save space right now, plus the y component squared. Okay, so this is our x, and this is our y. Okay, now when we do that, we get approximately 184, and this is miles per hour. Don't forget those labels. Okay, now how do we find the true bearing? Well, the true bearing comes from r, comma, theta. Okay, so really though, our bearing comes from the theta part itself. So theta, remember, we can get from tangent theta, which equals y over x. Okay, so again, if I were to put this in, we would actually be doing the inverse tangent of this 175 sine 50 plus 35 sine negative 30 all over 175 cosine 50 plus 35 cosine negative 30. Now it's inverse cosine. You're going to do all of this in your calculator. Remember, you need to be in degrees because that's what we're in. Now, when you get that, okay, you get approximately 39 degrees. But let's remember, 39 degrees would be right here. Remember, 39 theta is going to be from 0. But when we actually do a true bearing, we're supposed to do it from the y-axis. So if we do it from the y-axis, so I'm going to put a star here, y-axis. This is right here, this is x-axis. So the y-axis, you got to do it from the y, so actually it's going to be, this would be north, right? And then if we go this way, it would be, instead of 39, it's going to be the opposite, which is 51. And we're going towards the right, which is east. So that's another way that we can do that problem from last time. Okay. Let's look at some new stuff here. The unit vector. The unit vector is a vector with magnitude of 1. Any non-zero vector divided by its magnitude is a unit vector. If v is a non-zero vector, then v over magnitude is a unit vector in the direction of v. Noting that magnitude is always scalar, so it's a number, guys, and that dividing by a scalar is the same thing as multiplying by its reciprocal. A unit vector from any zero vector v can be found by multiplying by 1 over the magnitude of that vector. I'm going to show you what that looks like in an example in a minute. But if we do this process, it's called normalizing the vector. So what we're doing is we're taking any vector of any magnitude and we're actually shrinking it down to the unit circle. Okay, so by multiplying by 1 over the magnitude, we're shrinking it down exactly to the unit circle. Alright, so let's do that now. So the first thing we're going to do is find the magnitude, because remember, we're multiplying by 1 over the magnitude. So the magnitude of v is the square root of that -5 squared plus 12 squared. Okay, when you do that out, we get 13. So next, remember what it looked like, so I'm going to put a line there, was v over the magnitude of v, which really is in terms of 1 over the magnitude of v times v. So that's what I'm actually going to put in there. Okay, so I have 1 over 13 times the vector -5, 12, which means that our unit vector is going to be -5 over 13 times, or comma 12 over 13. Now, is it the unit vector? Well, think of this. The unit vector means the magnitude is 1. So if I really quickly try to find that magnitude there, okay, I'm going to try to find that magnitude. Remember, that's the square root of -5 over 13 squared plus 12 over 13 squared. Let's see, is it magnitude of 1? It is the unit vector. Awesome. So note that since a unit vector has a length of 1, multiplying a unit vector by the magnitude of vector v results in the vector v itself, providing the unit vector has the same direction as v. Okay, so the magnitude of v times the unit vector equals v. So the other way around, if we did this unit vector times the magnitude, we would get back to vector v. Makes sense. All right. Principal unit vector. So, of all the unit vectors, 2 deserve a special mention, and they label these vectors as I and j. So I is your unit vector of 1, 0, so what lies on the x-axis. And the j is 0, 1, the unit vector 0, 1, because it lies on y. Okay, so knowing that this are special vectors, we actually can do decomposition by saying that any vector v1, v2 is the same thing as v equals v1 times I and v2 times j. So think of v1 is going to be whatever number times 1, 0, and then v2 times 0, 1, and we get our vector v1, v2. It's just a way that we can think of graphing these vectors to the unit. Alright, so that is what we're going to do right now. We're going to have a vector with initial point to -6 and terminal point -6, 6, and we're going to write it in terms of I and j. Okay, so keep in mind that when we do the terminal point and the initial point, so this would be x initial, x component 1, no, this is y, sorry, y initial. That's why it's the initial, right guys? And this is x1, y1. And when we actually combine these guys, we subtract our x's and subtract our y's. So what we're going to do is say, I'm going to go -6 minus, why did I put a comma, minus 2. Okay, and that would be my new component x. And then I have 6 minus -6, and that's my new component y. And actually, because these are vectors, I should do that. Okay, so don't forget that this is our I and this is our j. So I can now rewrite that as -8i And really what we're doing is we're adding these together because it's our component. Okay, so remember back here, the vector v1, v2 is the same as v1i plus v2j. So there is my I, there's my j, and I'm going to add them together. Alright, so now we're going back to some basic operations, just like we did earlier in dealing with vectors and everything. We're talking about operations that work together. So if we were to add two vectors, okay, this is what we're really doing. We're adding the first components, adding the second components. Same thing with subtraction. Okay, subtracting, subtracting. And of course, k, remember, is a constant, so it's scalar multiplication. Same idea. All of this works. Okay, so we're going to do some of that algebra now with 3v plus w. So 3v plus w. The first thing I want to do is actually put these vectors out. Now, as you can see, the vectors are already in terms of I and j. So remember that. So if you have to do this again in the future, you might want to switch it to I and j first and then combine them. So what we are doing is saying 3 times 4i minus 2j plus negative 3i plus j. Guys, we can think of this like normal algebra. We're going to distribute that 2, or that 3, so we get 12i minus 6j minus 3i plus j. So we end up with 9i minus 5j. And we're done. So that is 3v plus w in terms of I and j. Alright, so we're going to get some physics into this almost. Using vectors to model forces. We conclude this section with a classic example which demonstrates how vectors are used as modeled forces. A force is defined by a push or pull. The intensity of the push or pull is magnitude. So that's where that comes in. The intensity, the tension, is magnitude. And is measured in newtons in the SI system, or pounds in the English system. So let's just keep in mind what system you are using for units. Okay. Alright. So we have a 50-pound speaker is suspended from the ceiling by 2 support braces. One of them makes a 60-degree angle with the ceiling, and the other is 30 with the ceiling. What are the tensions? So remember, what are the tensions means that we're finding the magnitudes. Okay. So the first thing I want to do is draw this out to make sure I can picture what it looks like. So in general, we have our ceiling. So we have our 60 and our 30. So let's do 60 here, 30 here, and here is our weight, 50. Alright, so we're looking at 3 forces, guys. We have our braces and our weight. So if I were to think of this on a coordinate plane, because that's how we use vectors, right? Where the center is where all of these come together, we're looking at, we're going to call it T1, this tension 1, which has a 60, I'll do that in a minute. We have a tension 2, and our weight is going straight down, and I'm just going to put that as W. Now, I had started to write 60 there, but I am incorrect. This is why I paused. Because if you remember, 60 was right up here with the ceiling. So imagine this ceiling right here, right? This is 60. So would this be 60? No. This would be 60 down here because of alternate interior angles. Like our ceiling is going to be parallel with where everything meets. So if this was 30 right here, that means 30 is going to be down here. Okay, so let's keep that in mind. Alright, so our tensions are our magnitudes, right? So the thing is, what I want you guys to keep in mind is that if the speaker is to remain stationary, that means all the tensions must balance out. Okay, what that means is that our W plus T1 plus T2 must equal 0. If it equals anything else, it's not going to hold it up correctly. Okay? So to balance out, we have to have everything added together equals 0. Okay? Now, what I also want you to remember here is this weight is a straight line down. And this weight weighs 50. So we know that the magnitude of W equals 50. Now, we're going to change everything into vectors so we are able to do this addition. Okay, so if we have the magnitude of 50 and this vector is actually on the y-axis, okay, so remember this is J, but it's going down in the other direction. That means that W is our magnitude times 0, negative 1. Okay, we're going to use our unit vector to help us with this one. So that means W is the vector 50, nope, 50 times 0 is 0, comma, negative 50. There we go. Perfect. Okay, so we got V down. Now we need tension 1 and tension 2. So let's look at tension 1. So tension 1, we have the magnitude of tension 1 times the vector. Now, in this case, we don't have our vector yet, but we do have a theta, which means we could go back to vectors in terms of theta. So that would be cosine 60 sine 60. Well, this is great because these are unit circle stuff, so we actually can do our unit circle on there. So we get cosine of 60 is 1/2. Sine of 60 is square root of 3 over 2. But again, we have to put that magnitude in there so we can add all of these together, right? So I end up getting magnitude of tension 1 all over 2. And then tension of 1 square root of 3 over 2. Perfect. Now we're going to do the same thing for tension 2. I'm going to put it over here, guys, so I can leave room for myself. Magnitude. Again, we have our cosine. Now, be careful though, remember, because our theta is always from 0. So if this is 30, all of this is our theta. Okay, so if this is 30, that means our theta is 150. Alright, so of course use your unit circle, all that stuff. I'm going to do this right out and say because that x component is going to be negative square root of 3 over 2, but I'm going to multiply that magnitude out already just to save space, okay? Square root of 3 over 2. And then sine of 150 is 1/2. So I end up with magnitude of tension 2 all over 2. Okay, sorry, I just skipped this step right here to save room, guys. Okay, so now we have everything in vector form. So we can go back to our W plus tension 1 plus tension 2 equals 0. Okay, so let me write that out. We get our 0, comma, negative 50 plus T1 over 2, comma, T1 square root of 3 over 2 plus, so much writing, guys, right? Negative magnitude square root of 3 over 2, comma, T. Alright, perfect. And remember, all of this equals 0. Alright, so we're going to do our addition, right? We add all of our x components and all of our y components. Now, guys, when I add them, I'm not going to put it all in one vector yet. I'm going to look at different elements. So when I say the x component of it, I'm going to say element 1, okay, because I don't want to get confused with things. So element 1, which would be 0, so I don't need to write that down. Then it would be magnitude of tension 1 all over 2 plus this, so I'm just going to put that subtraction in there, minus magnitude tension 2 square root of 3 over 2. And now what I actually could write this different is this being 0 is also the vector 0, 0. Okay, so that means this element 1 equals 0, and element 2 I would get negative 50 plus magnitude tension 1 plus magnitude tension 2. Whew, and that equals 0. Okay, how does this help us? Well, think of this as systems, guys. We have two parts that we can actually help solve each thing. So actually, what I am going to do first is I'm going to move all this over. Now, if we put this together, right, multiply by 2, that 2 disappears. So what actually happens is when we simplify this, we get magnitude of tension 1 equals the magnitude of tension 2 square root of 3. Okay, think about that algebra right now. Now what are we going to do with that is we are actually going to replace that now, substitute that in for tension 1. So I get negative 50 plus magnitude tension 2 square root of 3 square root of 3, right, because both of them are right there, all over 2 plus magnitude tension 2 all over 2 equals 0. Okay, let's do some algebra here. I'm going to move that 50 over. I get tension 2 times 3 all over 2 plus tension 2 all over 2 equals 50. Now guys, see, I'm running in a room, so I want to make sure that you understand this algebra. So I'm going to multiply both sides by 2, so that gives me 4 tension 2 equals 100. Get rid of 4 by dividing. That means that tension 2 has the magnitude of 25. Remember, that was one of the answers. We wanted to know the magnitude, the tension, the actual tension. So in this case, that second brace is 25. Okay, now we're going to use that and bring this back to help us find tension 1. Well, tension 1 equals tension 2, which we know is 25 times the square root of 3, right? Because we just plugged it in here. Now there's nothing else we can simplify, and we are done. We don't need to have any units right now, just for the fact that we don't know what they want for units, so it's okay just to keep it as is. All right, and we're done.